Morning, everyone. So I wanted to flip our way through our energy slides again. You may be using this lesson here as an introduction to what you're going to be facing in this option, or maybe you finish this option. Hopefully the summary will be helpful for review. So starting off with section C1 here, let's look over some of the big ideas. First one, when we're looking at energy sources, for it to be useful, it has to be able to release energy at a reasonable rate, not too fast nor too slow. Nuclear reactions tend to be a little bit too fast to work with safely. Rainwater has a lot of gravitational energy being up in the skies, but as the rainwater falls, it gives off energy way too slowly. Neither of those are useful energy sources. It's also an added benefit here if we have a source that actually produces minimal pollution. We always want to be thinking about our environment. Moving on to our second big idea here, although we talk very often in science about conservation energy, E in is equal to E out, energy cannot be created or destroyed, turns out every time we transform energy from one form to another, we always lose a little bit of heat to the surroundings. That heat there ends up sort of dispersing our concentrated energy source here, actually degrading the quality of energy. There's less energy that's actually available for useful work. How come we rely on fossil fuels, non-renewable sources so heavily is because burning these fossil fuels give us really high quality energies, even though I know these can't be replaced. So we're going to take a look at fossil fuels more so in section C2 and work onwards from there. There's a constant push to work towards more renewable sources here. Renewable sources here can be naturally replenished on our time scale. We know eventually our fossil fuels will run out. We want to have other alternatives available. Moving on to section C2, we're going to focus more so on these fossil fuels. First big idea is fossil fuels are actually formed by reduction of biological compounds. So living creatures from long ago, they were made out of organic elements here. It tends to lose oxygens way faster than C's and H's. So upon a reduction, we end up forming hydrocarbons, and those ones here actually form our coal deposits and petroleum deposits. We start off with two comic strips here with coal. Let's imagine a swampy environment here where we have large plants here. As they die off, they get sort of covered over with a layer of dirt, millions of years here underwater as well. Under high pressures at high temperatures, they end up forming coal deposits. Primarily, they're actually carbon. Let's compare that to a petroleum comic strip here. Very similar, but this time instead of being land plants, this is actually oceanic creatures here. When those creatures die off, they get covered over in a similar fashion, sand and silt, lots of water. Those high pressures will end up changing them, reducing them into what we nowadays use as petroleum. The petroleum that we actually dig up from the oceans, unfortunately, are a whole mix of different compounds. So what we need to do is we actually need to separate them. One technique that we saw in our organic chapter was separating them via fractional distillation. So what we're going to do here is we're going to dig up crude oil out of the oceans. It's a mixture of carbons from C1 all the way to C200. First thing that we're going to do is we're going to heat up the crude oil, and we're going to actually vaporize all of them. Long chains, short chains, all puts in the gas state. As these nonpolar molecules try to travel through this fractionating column here, we're going to find the relatively longer chains. We're going to have stronger London forces. They're going to have higher boiling points. As they move away from the heat source, they're going to condense first. The ones that are actually shorter are actually going to be able to vaporize a little bit more. They're going to climb higher and then get condensed at their separate layers. C1 to C4 is actually still a gas under regular pressures, so those ones they don't condense at all. So based on our organic chemistry here, you should be able to explain why the short chains rise higher, and therefore we're managing to separate this crude oil into different fractions. As we look at different fuel reserves here, there's a quality of fuel here known as knocking. This actually started off being named when engines would actually make a knocking sound. It was actually a symbol that the fuel was actually not a good quality fuel here. The fuel would actually auto-ignite. The pistons would not be in their maximum rhythms, maximum locations to deliver powers to your car, and actually might damage your engine as well. So what we do is we come up with a octane number scale. This is actually the rating that you actually see at gas stations. Yes, higher quality fuels will have higher octane numbers, although be careful, some cars are not designed to burn high quality fuels. Pretty much the conclusion out of here is you want to use the fuel that your car is designed for. Fuels will burn most efficiently when they're supplied with the right amount of oxygen. This is predicted by the stoichiometry in a balanced equation. If you have too little oxygen here, we call it a rich fuel mixture. Way too much fuel versus how much oxygen there is, that leads to something called partial combustion or incomplete combustion. Instead of fully getting CO2, we get carbon. We get a very dirty flame with unburned amorphous carbon. We also tend to get carbon monoxide, which is a toxic gas. If you have too much oxygen, that's not good as well. We have a lean fuel-to-air mixture. That's actually what causes knocking. So as you start looking at this rating here of octane number, we find experimentally straight chain hydrocarbons are prone to knocking, whereas if I can increase the branching, it actually helps the fuel be higher quality, actually resist knocking a little bit better. Octane number here is the scale. We find heptane, which is a nice 7-carbon straight chain molecule. That one knocks really much, so we're actually given an octane number of 0. We find this more branched form here. It's actually an octane, but it's actually a sort of branched form of a pentane here. This one here, isooctane, actually burns really, really well. Not much knocking. That's actually given a scale of 100. So when you're at a gas station, let's say I'm looking at a fuel that has octane rating 94. That fuel there, it's not made of heptane or isooctane, but if I made a mixture that was 94% isooctane, 6% heptane, the fuel that we get from the gas station burns as this mixture here. Isooctane was the standard for long periods of time. There are now chemicals that actually burn even better than isooctane. I think methanol has an octane rating of 106, 107. That's totally okay. So to improve the octane rating here, what we want to do is we want to increase the branching as much as we can. I'm going to demonstrate to you 2 chemical techniques. One is called cracking, and the other one is reforming. First, with cracking. Cracking involves taking larger molecules and breaking them down into smaller molecules. It can be done via high temperatures, high pressures. It can be done using steam. It can be done using catalysts here. But all in all here, we're taking longer chain molecules and we're breaking them up into smaller molecules. As you start breaking them up, we're going to look in detail. You can only always form one alkene products. There simply are not enough hydrogens for you to make more than one. The rest of them have to be alkenes. So the types of cracking that we're going to investigate using heat treatment or pressure treatment here, using steam. Sometimes you use zeolites. Zeolites are natural minerals, aluminum and silicon here, and they are catalysts that actually allow longer chains to crack into smaller chains there. And once we get those smaller chains here, we're ready for the other process called reforming. We just said straight chains tend to have very low octane numbers. If I can somehow isomerize them, if I can increase the branching, I'm going to increase the quality of that fuel there. So in this case here, we're going to use aluminum chloride catalyst here. I'm going to isomerize some of the straight chain here into branching here. I'm going to separate off some of these branched alkanes here. This will now be a higher quality fuel, and then I'm going to recycle them, isomerize them more to improve the octane rating. Reforming can also be in the form of cyclization. Turns out as I end up forming rings, or even as I end up forming aromatic compounds there, that also improves the octane rating. That'll make a better quality fuel. Now, as you look at carbon deposits here, coal has one major disadvantage. It is a high-quality energy source, but unless I have a large-scale power plant, I can't really extract the energy really easily, right? You can't put lumps of coal into your car and expect it to actually burn effectively. What we want is we actually want to convert coal into either gas form or liquid form. Liquids, ideally, because they're easier to store, easier to transport, safer to work with. So let's just have a look here. We can actually gasify coal. Coal is primarily going to be carbon here. Upon reaction with water, it actually converts it into a mixture called synthesis gas. This hydrogen carbon monoxide mixture here, this one here still has the energy that the coal has, but being in the gas state here, it's a lot easier to burn. We can also liquefy them here. We're going to basically take that synthesis gas mixture here, convert them into hydrocarbons. We're primarily looking for C5 to C10. In this case here, I actually want it to be liquid, so we need at least N to be 5. C1 to C4 are still gas. So when you liquefy them there, this is basically the gasoline that your car engines can actually run on. As you burn these sources, whether in the gas form or the liquid form here, we always want to worry about a carbon footprint, which is actually a measure of the total amount of carbon dioxide that we're actually releasing per year. We always want to be thinking about our environment here. Carbon footprint is usually expressed in equivalent tons of carbon dioxide. Carbon dioxide is believed to be one cause of global warming. That's given a global warming potential of 1. Your textbook calls this a greenhouse factor. The most abundant greenhouse gas is actually water, because it's actually very, very common in our atmosphere, but water is actually 10 times not as bad as carbon dioxide. You need 10 waters to have a similar global warming effect as CO2. whereas methane, not as common, but just one molecule of methane is as bad as 30 molecules of CO2. So we want to always be conscious of our carbon footprint here in thinking of our environment. As we step away from fossil fuels here, C3 and C7 started looking at nuclear reactions, nuclear power plants. What we're going to do here is we're going to start off with heavy nuclei. All our nuclear power plants, they perform fission on heavy nuclei, breaking them up into smaller particles. This breaking here actually increases something referred to as the binding energy per nucleon. We actually want to take a look at what is this binding energy. The nuclei, as I know, we're going to call them nucleons. They're made out of protons as well as neutrons here. All the protons are positively charged. They all hate each other. They're all going to constantly repel away from each other. How come the nuclei can stay in such a tight environment? It's actually because of the strong nuclear force. It's actually related to this binding energy that we're going to talk about. So this binding energy here is the energy required to break up a nucleus back into free protons and free neutrons. If I can somehow increase the binding energy, I'm actually producing a more stable product. So we're going to see this graph here a couple of times here. It plots the average binding energy. I'm going to divide it by nucleons. I'm going to plot the number of nucleons along the horizontal axis here. I actually find the higher the binding energy per nucleon, the more stable it is. The most stable isotope I have is an iron isotope. That one here is going to have the highest binding energy. So fission reactions here are going to take really heavy nuclei like uranium, break them up. It doesn't need to go very far, but as I head towards that direction, as I increase binding energy, that energy can be radiated away as an energy source. So taking a look at this binding energy here, binding energy actually comes from something referred to as a mass defect. It turns out when I compare the mass of a nuclei after it's formed, and I minus the mass of the individual nucleons, the protons and the neutrons, I find that the nuclei is actually lighter. That shouldn't be. Where did all that mass go? What the mass actually has converted to is actually it's converted itself to this binding energy. We can use Einstein's equation of E is mc squared. Overall, the mass is conserved. This binding energy ends up holding the nuclei together. So we're going to practice through a few of those calculations. For a fission reaction here, again, it involves taking heavier particles. It breaks them down to daughter isotopes that are smaller. Because the daughter isotopes have a higher binding energy, they're more stable. The extra energy gets radiated away. Our nuclear power plants are designed in one of two ways. A uranium-235 power plant here. We fire really slow-moving neutrons here at a uranium-235. We cause this to undergo fission, breaking up into many different daughter isotopes. Very often, this fission reaction ends up releasing neutrons as well. What we want to do is we want to control how many neutrons ends up being released, because we don't want 1 to trigger 2 and 2 to trigger 4. We don't want this to spiral out of control too quickly. The critical mass is the minimum amount of uranium-235 that we have, so that even though I'm controlling the amount of neutrons that are being released, the one neutron that is on average emitted has a good chance of running into something else, so it can actually be self-sustaining. Once your fissionable or fissile uranium-235 is used up, it mostly gets converted into plutonium. The question here is, can I put the plutonium to use here? This is our third big idea. That you actually have nuclear reactors actually designed using plutonium. This is an otherwise waste material out of our uranium reactors, but we managed to harness plutonium. Plutonium has its advantages that it doesn't need the enriching process that we're going to see for uranium, but we're actually managing to recycle some of this plutonium product. Back looking at uranium here, we're going to be dealing with uranium in the compound UF6. This uranium here can still be either the 235, the radioactive form, or the 238 form. The reason why we like this UF6 compound is most uranium compounds are actually ionic. So let's just compare it to another ionic compound, UO2. UO2 is actually an ionic compound. It's a lattice made out of uranium ions and oxide ions here. It's a nice crystalline solid. It stays solid upwards of 2800 degrees or so. The UF6 that we look at here is actually a covalent molecule. It's uranium here. It has a lot of polar bonds here and trying to bond to fluorine. It's octahedral. This octahedral geometry actually cancels out the polarities, so overall it keeps me nonpolar. But because these fluorines here are so electronegative, they're going to be so negative that when a UF6 here is close by another UF6 here, it actually limits the amount of intermolecular force in between. This one here actually sublimes at some 56 degrees. It skips the liquid state altogether, and something that's slightly hotter than room temperature, it already is gas. Working with gases through a power plant is a lot easier than working with chunks of solid. Only problem with this UF6 here is we still need to have UF6 using the lighter isotope. The lighter type is radioactive. The more common, 99% of it is actually 238, is actually non-fissionable. So what we need to do is a process that actually converts the 238 form and enriches it to form a 235. One way to do this enrichment here is through a diffusion or effusion kind of law here, by pushing it through a permeable membrane here. It turns out here that the uranium-238 isotope in UF6 will be slightly heavier. That would mean that the speed at which it speeds through tiny pores here is actually a little bit lower than the lighter isotope. We're going to calculate this one here. It's only by a matter of 1.004. It's not by much. But what I can do here is I can actually cycle this through many, many times to produce the enrichment that I have. So here's a mixture. The gas is UF6 that contains both the uranium-238 and uranium-235. Because the 235 travels ever so slightly faster than 238, I'm going to gradually, as I push it through this membrane here, gradually get a higher and higher concentration of 235. I do need to repeat this many, many times. The other way that we can do enrichment here is using a centrifuge. Because the heavier masses here get thrown to the outside of the centrifuge here, we can sort of collect the uranium-235, slightly smaller radius here, and we can actually taper off the 235 type away from the UF6. As we start looking at nuclear power sources here, we always want to be thinking about the risk. Risk can come to us in multiple forms. The health effects from the workers that are using it. The wastes, which tend to very often be radioactive themselves. What do we do with it? If the reactions spiral out of control, it can lead to something called meltdown. And always a worry, what if the science here is later on used for weaponry? Looking at health effects in general here, the alpha and beta and gamma types of radiation in general, they can actually interact with your body and actually damage cellular tissue, DNA structure. One way of doing that here is it actually ionizes some of the water. Either that or it ends up producing various radicals, hydride radicals, hydroxide radicals. All of these are high energy enough to actually damage living tissue. So you just need to be careful of that. Oxide is also another really common radical of that. What we've been focusing so far, our power plants have been doing fission, taking heavier isotopes and breaking them up to form more stable isotopes. It turns out if I could somehow take really light isotopes, join them together, that also increases binding energy per nucleon. The added stability that I get, I can radiate away any extra energy as a useful energy source. Unfortunately here, this one here has not been harnessed on the Earth so far. It is promising though. The fuel is very inexpensive. So hydrogen, helium is really, really abundant. It doesn't end up producing a lot of waste that we don't really know what to deal with. This one here is sort of a holy grail in science here. We haven't managed to make it viable just yet. Where have we seen fusion? We see fusion here in deep space when we take a look at stars. Stars are primarily made out of hydrogen, helium, and some other elements. The stars here, they're actually burning with fusion. Hydrogen sources, they're converting hydrogen to helium. The reason why stars can sort of be self-sustaining and give off so much energy is actually through a fusion reaction. How do we know fusion happens in stars here? We can do our chapter 2 stuff. I can point a spectroscope here at the star. I can track the emission spectra. As the electrons on the hydrogens get excited, as they end up falling, they end up giving off unique bands of color. And remember, this one here acted as a fingerprint for the element. This one here is a hydrogen fingerprint here. As I compare that to a helium, I can actually compare not only which elements are present in the stars, but also the abundance of that element in the star. So back to our sort of power plants here, designed using fission. Depending on the waste, depending on its half-life, how long it actually sticks around for, it actually decides for me what I do with it. So just generically looking at the different types of radiation, we have alpha, beta, gamma. Alpha particles here are the least penetrating here. They can be stopped by a simple piece of paper. Beta particles are roughly 100 times stronger than that here. We're going to need maybe a couple meters of air. Gamma rays are yet another 100 times stronger than that. We might need to encase it in a few meters of concrete. So as we start looking at storing and disposing of waste here, it really depends on the type of radioactivity as well as how long it takes for this to decay away. Turns out on the Earth, 90% of our waste is referred to as low-level waste. It only releases really low-energy alpha and beta. This would be a very a common source here is the workers that are wearing lab coats and gloves. Inevitably, they end up getting covered with some nuclear material, but it's very low-level waste. This one here, if the radiation level is still fairly low, I can keep it on site until the half-life sort of dies away, or I can bury it in very shallow pits. The parts that I'm worried about is the high-level radioactive waste here. It's actually a very small portion of what we have on Earth. So if I have a nuclear power plant here, as I use up my fuel rods here, the question is, what do I do with that fuel rod? That's going to be a lot of really concentrated nuclear energy. We really haven't found a really good solution to this here. Storage and disposal is problematic here. Currently, what we do is we vitrify it. We sort of encase it in glass. We sort of seal it into many layers of concrete, and then we basically bury it deep down for a whole millennia, hopefully in a geologically stable area that is not susceptible to earthquakes. I know not the best solution, but that's the one that we have so far. Moving on now, we're going to compare C4C8, taking a look at solar energy. Solar energy is actually our ultimate energy source. Even if you think about fossil fuel sources, that was plants having stored the sun's energy way back. It's just over millions of years it has been reduced. As you compare sort of nuclear energy here, usually fission, fusion reactions here, nuclear power is converted to heat, then is converted to kinetic energy of particles, and only then is converted to electrical. We talked about in section C1, every time you do one of these energy transformations, we lose a lot, the quality ends up degrading away. Compare this to the solar panel case. Solar panel directly takes light energy, could be from the sun, could be another concentrated source here, converts to electrical. This will have some losses as well, but only one transformation. It means I have more that's useful for me. This is actually how we design our photovoltaics. We're going to see semiconductors in a later section here. First thing we're going to do is we're going to look at a working model. So if I have producers here, plants, they're actually going to manage endothermically to absorb light's energy, store some of that energy into higher energy molecules. This is one example of a reaction called photosynthesis in producing glucose, a sugar. Consumers will then eat these plants here and actually burn these sugars for their energy sources. Question here is, how do the plants know how to do this? Plant cells have a very special organelle known as a chloroplast. Chloroplast inside, really easy to recognize. There's all these stacked discs here. These discs here are filled with a molecule called chlorophyll. This chlorophyll is the chemical that's actually responsible for absorbing light. Let's take a look at the chemistry first. Chlorophyll is a molecule, along with other pigments, that have a conjugated electronic structure. So let's just have a look at a few different molecules here. What these ones here have in common is actually they have alternating single and double bonds. It's that conjugation that actually allows it to absorb energy. So chlorophyll, although it has a really complicated structure, it does definitely have that conjugation, the single, double, single, double. Those double bonds here would otherwise be pi electrons. What's actually happening is, as this light here is actually given to these pi electrons, they actually excite the pi electrons up to the pi star energy level. As your length of conjugation gets longer and more extensive, the amount of energy needed to do the excitation decreases. So we see going from just having one double bond to a slowly longer and longer conjugated system, you notice that the wavelength gradually gets higher and higher. Now remember here, our chlorophyll actually looks green to us. It's not because it absorbs green, it's because it absorbs the opposite of green here. The green is actually the complementary color that we end up seeing. So what we do now is we actually design our solar panels or photovoltaics to mimic what chlorophyll does. So again, more in the chemistry first. So we're going to have a look at semiconductors. We're going to primarily be looking at silicon here. Photovoltaics utilize these semiconductors here somewhere in between metals and non-metals here. What we have here is an energy diagram. Imagine energy axis going down. We're going to start off with metals. Pretty much the electrons in the valence band and the conduction band, there's not much of a gap. Metals are very conductive. It's pretty easy to promote these electrons up. Semiconductors are sort of medium ionization here. The electrons down here aren't good to conduct. You need to be able to excite them enough, jump this band gap to actually get them up into the conduction band for them to carry a current. Insulators are the ones that have the biggest gap here, the highest ionization energies, so those ones are going to be least conductive. We're going to focus mainly on comparing metals and non-metals here. For metals, we notice they have delocalized electrons. Although the positive ions are just vibrating in place, the electrons are just moving throughout the entire structure. We need charges that can move for conduction. As I increase the temperature of a metal, the vibrations here get to be a little more dramatic. It causes more internal friction. It doesn't allow the electrons to flow as freely, so conductivity drops. For semiconductors, however, using that sort of energy level diagram, at first, all the electrons on the valence band, they need to be promoted up to actually conduct. as I heat up a semiconductor, those electrons get pushed up to the top, and then they can carry a current a lot easier. So for semiconductors, the higher the temperature, generally the conductivity increases. We can actually improve the conductivity even more by doping the semiconductor. Silicon is in group 4. What we can dope it with is elements, either group 3 or group 5. Those ones there are going to have a different number of charged particles. Let's start off by doping with group 15 elements. So I have just pure silicon. Every silicon on average has 4 valence electrons. I'm going to dope it with a group 15 element like phosphorus. You don't need a lot of them, but I hopefully have interspersed it through the silicon sample. Phosphorus would actually have 5 valence electrons. It has 1 more electron than the other silicons do. That added electron will increase the number of charge carriers, allowing for conduction. So this electron can end up moving around, creating what's referred to as an N-type semiconductor. Next, what we can do here is a P-type semiconductor. Let's dope it instead with a group 13 element. A group 13 element here, like boron, it only has 3 out of silicon's 4 valence electrons. Having this hole here, this is going to be a net positive charge. Silicon can then transfer its electrons over. The hole would then move over, and electron can then move over to fill that hole. The hole moves over. We can also think about these positive holes moving, increasing the number of charge carriers as increasing the conductivity. What's neat here is once we have N-type and P-type semiconductors, we can actually join these two types together. We have a P-N junction here. The N-type semiconductor has an excess of electrons. The P-type semiconductor has an excess of holes. At first, the electrons will jump the gap to try to fill the holes. We can track the electrons going down this way as holes going upwards. Eventually, we're going to get a layer that is really positive on top, really negative on the bottom, creating called the depletion layer. Then if I have extra electrons here, they won't want to go to the other side because I have an electric field that's sort of set up against it. What we're going to do then is we're going to connect an external circuit. Since the charges don't want to go through then, let's use our light sources. Let's create yet more electrons. Because the electrons don't naturally want to go through this depletion layer, we form an external circuit and allow the electrons to actually pass through the external circuit. Whenever electrons are traveling in one direction, we get a direct current, and we manage to taper off the electrical energy there. So solar panels here actually maximize this sort of PN junction design here, and it's just an array of these PN junctions. We can even mimic our photosynthesis in plant cells even more with what's referred to as DSSCs, dye-sensitized solar cells. Very similar here, we're going to start off with the anode, the site of oxidation. We're going to actually use our dye to actually absorb light. The dye gets excited into the dye star form. It ends up ionizing, dropping off its electrons to titanium. The titanium here, its electrons here have been created because it's absorbed light. It can't pass through this PN junction here, but we've allowed an external circuit to actually pass through. So what ends up happening here is the electrons, once they're passed to titanium, they can be passed through the external circuit down towards the cathode. The cathode is a site of reduction, so usually what ends up happening is we're going to have our iodide ends up picking up those electrons. In this case here, as the electrons actually pass through, that's actually mimicking an analogous structure called the electron transport chain in the living analogy. Okay. I mentioned here the I- ends up doing reduction. We expect to see the electrons on the left-hand side. That's exactly what happens to sort of finish off completing the circuit, and therefore it ends up reducing the dye back, and now it's ready to absorb more light again. The reason why we use TiO2 as nanoparticles is because they have really high surface area, so the dye is going to cover all these nanoparticles, absorb maximum light to actually transfer most electrons. The advantage of DSSCs over just a generic photovoltaic, the huge surface area of the nanoparticles make it more efficient. They're typically cheaper to manufacture. The efficiency of a photovoltaic tends to drop, and DSSCs tend to work more in low light conditions. So that's how we actually looked at a plant system, and we actually mimic it using photovoltaics or DSSCs. Next part, what we're going to do here is what if we take those plants and what if we actually transfer them into biofuels? So what we can do is a process called fermentation. I take those simple sugars that plants produce very naturally here, and these ones here are fermenting. It can actually create ethanol. Ethanol can be used as a fuel itself. It can be burned directly, although your engines have to be designed for it. But ethanol here by itself has some advantages and disadvantages. The advantage here is we say ethanol is actually carbon neutral. Sure, every time you burn something, it ends up releasing CO2, but where did the CO2 come from? Photosynthesis took CO2, converted it into sugar. the sugar was converted to ethanol. Ethanol just replenishes the CO2. That CO2 isn't any extra CO2 I would have had anyways. We say roughly it is carbon neutral. It also reduces our dependence on oil, so therefore it gives you another alternative. Some disadvantage of using ethanol or other biofuels here, it has a lower specific energy or energy density. Specific energy will actually calculate, it's the energy per mass. Energy density is energy per liter. Turns out we actually require burning more fuel to actually generate the same amount of energy that burning gasoline does. Ethanol here, because it has that hydroxyl group here, it tends to have hydrogen bonding, absorbing moisture from the air, which can lead to corrosion. Other disadvantage here is, although we had expected it to be carbon neutral, sometimes doing the conversion, fermenting enough of it, sometimes the carbon footprint is similar to having burnt gasoline itself. And I like this last one here with the food versus fuel debate here. Usually you grow crops for eating, but if you're now growing crops here and you're now diverting some of these crops here, this is going to be converted over to form biofuels to run your automobiles here. They're worried of the economics of it. Maybe it's going to drive up costs for poorer countries, and they're going to be more vulnerable for starvation. From a chemical standpoint here, the energy content in these vegetable oils, in these biofuels, diesel fuels here, they're very similar to combustion engines. However, one chemical problem is that they are too viscous. So looking back at our fractionating column here, we had separated them based on boiling point. We're going to find that as we zoom in here, gasolines typically use slightly shorter chain carbons. Diesel fuels, similar to our vegetable oils, biofuels, tend to be a little bit longer. Our vegetable oils here typically have this triglyceride structure. They are esters, which have really long R chains. It's actually these R chains that actually cause this one to be very, very viscous. So let's just have a look at some of these R chains. So this one here would be like a saturated fat here. Every time you have a double one, it actually kinks the molecule. That actually introduces some unsaturation. It makes the fat a little bit easier to digest. How do these R chains end up making things too viscous? So let's just compare a few different molecules here. We have tristerion here. This one here has really parallel chains. This part is definitely going to be nonpolar. The more surface that's actually exposed will actually increase the London forces in between. That actually gives this melting point here to be very high, strong intermolecular forces. Even if you increase 1 degree of unsaturation, create a double bond so they actually kink on themselves here. Very similar length chain, but you see that the melting point is way lower. So what we can do here chemically is, if our ester had a problem of being too viscous, I can try to do a process called transesterification. I'm going to react this ester that's too viscous, react it with an alcohol, trade it in for another ester alcohol. So let's just see a picture of how this looks like. We're going to convert something with really long chains to something with a shorter chain here. We start off here with our triglyceride. The long chains here, that's being too viscous. We're going to react it with methanol or ethanol. You'll notice that this reaction here is actually in equilibrium. What we can do is we can actually, reacting it with methanol, I'm going to try to replace some of these longer chains with a short chain alcohol. What I want to do here, these 3 chains here were all side by side, making it too viscous. As I sort of replace it with this alcohol grouping here, I end up still getting the R chain. We have the short chain from the methanol grouping, but you notice these 3 esters here are not connected. They're actually free to leave, and therefore the London forces are actually going to be weaker. Being in equilibrium here means I can add more methanol here, and I can actually shift the equilibrium over to convert for the less viscous ester. Last part of review here, we want to take a look at some global warming, some environmental impacts here. First thing we're going to look at, our big idea, is greenhouse gases. They typically allow solar radiation, which comes in shorter wavelength. As that light bounces off the Earth, it tends to radiate away as a longer wavelength light. So there's a picture of that there. We do have an atmosphere on the Earth here, and the greenhouse effect is a natural phenomenon where the atmosphere, it does reflect away some of the shortwave radiation, but primarily most of the light gets through. What we're worried about here is when that terrestrial radiation, after bouncing off the Earth, it gets reabsorbed by the atmosphere and then re-radiated back towards the Earth's surface. So what ends up happening here is some of the light actually gets through. We're worried about the part that actually re-radiates. Now, what you need to be careful here is greenhouse effect is actually a natural phenomenon. It's actually what keeps our global average temperature about 15 degrees or so. That's what's needed to actually sustain life. What's worrisome here is, especially burning a lot of fossil fuels here, carbon dioxide, methane, water, it's believed to actually re-radiate in such a degree here that it's actually increasing the temperature more than natural, and that's actually causing a global increase in temperature. So looking at a sort of statistic of how much greenhouse gases that we have in our atmosphere, we have our greenhouse gases like CO2 and methane here. These ones do that re-radiating back towards the Earth's surface, causing global warming. There are other things that can happen here is you may have other atmospheric particles here, especially polluted clouds here tend to reflect light. So if I can actually reflect some of that solar radiation, not let the light come through, that actually results in a phenomenon called global dimming. Right? This is a global issue, so it needs a sort of global solution as well. Again, focusing on the chemistry first. What is it about a molecule that makes it IR sensitive or IR active? It really depends on the covalent bonds. We learned from the spectrochemical section, covalent bonds here work more like springs. And basically here they're naturally vibrating, bending, and stretching. There's a couple different modes of twisting here. What's going to happen here is if I have a covalent bond that has a dipole moment, infrared radiation is the perfect amount of energy to cause this dipole moment to change, to cause it to actually absorb energy. So this carbon dioxide molecule, although nonpolar overall, because it does have a polar bond, is IR sensitive. The IR radiation, the important phrase is it changes the dipole moment. It can cause this stretching and contracting to happen a little bit more. And because of that here, the covalent molecules absorb the IR radiation. After they're excited, they're going to relax back to ground state. They're going to re-radiate, re-emit this radiation back to the Earth. So as we start taking a look at some general statistics here with the global temperature increase here, we're plotting parts per million of carbon dioxide versus the last 100 years or so. We see that there's a general correlation with as the CO2 increases, we're going to find that the global temperature also increases. What's nice on this chart here is it actually plots the seasonal variation. It plots, oh, we're hot in the summer times, cold in the winter times, but gradually though, there is still an overall increase. We can look more than just the last 100 years, look at ice core measurements here, actually go back hundreds of thousands of years here. There generally is a correlation between the CO2 content at that time and the gradual global temperature. What we're worried about here is within the last maybe 50 years or so, as we burned a lot of fossil fuels, the CO2 is increasing. The question is, what's going to happen to the global temperature? So different models here predict, some predict really big increases, some more moderate increases, but nonetheless here they do predict the global temperature is going to increase. The atmospheric gases that we're worried about that cause global warming potentially, again CO2 is a global warming potential of 1, that's set as our standard. The most abundant global greenhouse gas is actually water. It's actually not as bad, 10 water molecules for the effect of 1 CO2. Methane, one of those molecules is already 30 times as bad, but also not as abundant, so its contribution is a little bit less. What's the effect of these greenhouse gases or this global warming here? The oceans tend to become more acidic. We have melting of polar ice caps here. There's rising sea levels. It's changing a lot of our ecosystems, changing a lot of biological patterns, and it's leading to more frequent weather conditions. Let's take a look at the ocean acidification in more detail here. Normally, our oceans have a heterogeneous equilibrium. Heterogeneous because CO2 is in the gas state, aqueous state here. There's a natural healthy balance between the gas state and the aqueous state. Carbon dioxide in the aqueous state actually serves as a carbon sink. If the CO2 gets to be too high, it shifts the equilibrium downwards. The CO2 can temporarily store some of that CO2. Unfortunately here, as I increase temperature, water actually doesn't dissolve CO2 as well. It causes a push towards having CO2 in the gas, and then I can't actually sink away some of the CO2. So more gas in the atmosphere, more global warming potential. It's a vicious cycle. Also, oceans can get acidified here. We see CO2 here as a non-metal oxide. When non-metal oxides encounter water, this happens naturally even with rainwater, but definitely in our oceans, and ends up forming carbonic acid. Carbonic acid ends up releasing H+. Right? The sea level is gradually going to rise because we are melting more solid ice deposits. Water also expands slightly as we get warmer, so it's going to take up a little bit more volume. Here's a graph here plotting in the next 80 years or so. It's plotting how many centimeters is actually going to increase based on different modeling. It's not all doom and gloom. We can actually try to control our CO2 emissions. We can try to design our automobiles being a little more efficient so we're not burning as many fossil fuels, push towards having more alternative or renewable energy sources, reducing our dependence on our fossil fuels. We can do sort of a market-based control. I can put taxes on carbon. I can try to do that sort of control, or I can try to do a carbon sequestration. Sequestration is just a fancy word for capturing the carbon dioxide before it ends up leaving. Last section I'm going to overview with you here is looking at our redox chapter. We were looking at voltaic cells. Our voltaic cells here were primary cells here. They typically couldn't be recharged. We're going to look at different makeups that actually allow it to actually be rechargeable. So if you remember here, this was a half cell. It was a spontaneous reaction. Here we have copper ions swimming up close. The electrons always arrive at the cathode. The copper ions grab those electrons. They reduce on the surface. The electrode increases. We can't have a cathode without an anode. I assume that the anode for the time being is going to be the standard hydrogen cell. That way we can do all that standard reduction potential again. The chemicals were ideally supposed to give you a true voltage called an EMF, but it turns out as the ions just try to travel through the material of the battery, it takes a finite time to actually pass through. That actually introduces a little bit of internal resistance. If you do Ohm's law V is equal to IR, we actually lose a little bit of voltage, so the terminal voltage that we get off the battery is somewhat less than what the true voltage that we could have got from our electrochemical cell. So make sure you rehash some of these terms here. Electrons flow anode to cathode out of the external wire. We have a salt bridge to maintain electrical neutrality here. Anytime electrons are traveling one direction, I can taper off the electricity here as a voltage. Back in our redox chapter, we mainly did standard cells, which are at 1 molar conditions. We're going to introduce in this section called the Nernst equation. And what it does here is, as the battery ends up running, the chemical amounts start changing. That's going to change this trial KEQ value. As the trial KC value changes, that's actually going to decrease the voltage. The voltage is going to steadily drop to 0. 0 is when we're at equilibrium, when we actually have a dead battery. So I'm just going to flip over a few pictures of different battery setups here. This is our standard car battery. We have lead oxidizing, and we have PbO2 being reduced. As long as the lead and the PbO2 is encountering the H2SO4, it can actually react, it can discharge, it can cause electrons to flow one way. These two end up forming PbSO4 as a solid that ends up coating the plate. It actually prevents the PbO2 and the Pb from reacting any further. If I charge the system here, basically what I do is I run the reaction in reverse, cause the PbSO4 to convert itself back into PbO2, reveal more fresh surface for the reaction to discharge again. So what's important for you to just realize here is just given these equations, you should be able to identify who's oxidized, who's reduced. You can track a change in oxidation number. We looked at nickel-cadmium batteries. Again, be careful when it's the discharge cycle. The recharge will be the opposite of that there. We have lithium-ion batteries here. So we actually use lithium here as the anode side. It's the oxidation. We use a polymer electrode to actually transfer the lithium from one side to the other. And lastly here, we're going to take a look at a few fuel cell setups. The advantage of a fuel cell here is we're taking hydrogen and oxygen, which are really plentiful here, and you notice the only waste product, it doesn't even burn to produce CO2. We only have the hydrogen source, and ends up releasing just water. So one sort of engineering problem here is you constantly supply the hydrogen and oxygen, but if I can do this, whether in base catalyst or whether in acid catalyst here, I can cause the electrons to actually flow through the system. Fuel cells are not always just hydrogen, oxygen fuel cells. We can even create a methanol fuel cell. You have some corresponding reactions there. And we'll end off this summary here using a sort of bacterial fuel cell, my microbial fuel cell here, where we have an anode. We actually have bacteria here that actually perform the oxidation for us. It converts otherwise wastewater, otherwise organic matter. It causes a loss of electrons. Those electrons get passed over to the other side here. The bacteria have to work in an anaerobic environment. There's no oxygen. But this side we're actually using oxygen. So this side is definitely aerobic. It's going to need some engineering. Okay. So hopefully that's a nice summary of this option here. If you do have any questions, just let me know. Thanks, guys.